Something to do with who's introducing.
Yeah, that's fine.
It doesn't say Ian Walmsley, does it?
Yes, it does.
Why? Oh.
Good afternoon, ladies and gentlemen. I am Ian Walmsley, the Provost here at Imperial, and it is my very, very great pleasure to welcome for this special lecture Professor Donna Strickland of the University of Waterloo, who you will know, of course, as one of the recipients of the 2018 Nobel Prize in Physics. I am delighted to have known Donna for essentially all of her career, I think. We were both graduate students at the University of Rochester in the 1980s, so it's been great to catch up and share some memories from that time from next door laboratories. Donna was working there on the project that earned her the Nobel Prize, which was the development of the Chirped Pulse Amplification scheme that she invented together with Gerard Mourou, who was also a co-winner. She got for that work the first accolade, which was the PhD in optics from the Institute of Optics at the University of Rochester, having earned a degree from McMaster University in Canada earlier. That's her home country. She then went on to research projects at the National Research Council of Canada in Ottawa, at Lawrence Livermore National Laboratory in California, and at Princeton University in New Jersey. She joined the faculty of the University of Waterloo in 1997 and started a group there developing ultrafast laser technology for nonlinear optics. That's the topic of her talk today, and she will tell you some of her work and the latest developments that she has contributed to. She has, of course, won many awards through her career, such as the Sloan Research Fellowship, the Premier's Research Excellence Award, and a Cottrell Scholar Award. She also served as the president of the Optical Society in 2013, and of course is a fellow of that society. So we're delighted to welcome you, Donna, to Imperial College London, and look forward to hearing the research that you've been engaged in.
So first, let me thank Ian for hosting me, and everybody here at Imperial. It's been wonderful. It's a great visit. To all the graduate students that are here, I wish you the same luck as I had in grad school. I hope you all get as much fun out of your project as I did. So I'm going to talk to you a little bit. We went back and forth whether this was supposed to be my public lecture or my physics lecture. For those of you who might not be from physics, there will be the odd equation. But don't worry about it, because you don't really need to know the equations at all. So if you're not from physics, just let that go, all right? And I'm going to just start with these ones, because these are Maxwell's equations. And I have to supposedly stay in the light. Let me stand in the light. So as Ian said, we were both at Rochester, and the undergrads there every year would come up with new T-shirts, at least back in the days. And there's two that I remember well, but one of them was, in the beginning, Maxwell's four equations. And God said, let there be light. So that's why I'm going to start with Maxwell's equations. So if you don't know them, don't worry about it. But that's the main reason that I'm starting, just to say that it was this mathematician that got the physicists, the scientists, the optics people of the day to really feel at the end of the 19th century that light was a wave. And so here we are, close to a seashore. I mean, it doesn't matter where you are in England, you're close to a seashore. So hopefully that's from a Canadian point of view. So hopefully you've all been to the sea and know that waves, you know, the bigger the wave is, the more powerful it is, and the more power you feel it hitting you if you're on the seashore. And it has nothing to do with how far apart the crests are. It's how big the crests are, is how powerful it is. And so out of these equations, this is what Poynting came up with. I still haven't figured out why Poynting's vector is an S, except P is used so much, so, you know, maybe. But I don't know where the S comes from. Anyway, you don't have to, again, worry about the equations. But what this one down here is telling us is what I just said, that if you're talking about the power, and in this case, power per unit area, you're really talking about the amplitude of the wave. And so the bigger the amplitude, the more power per unit area. That's the important thing to get out of Maxwell's equations at this point in my talk. All right, so now comes the end of the 19th century. Everybody says Maxwell's right, all right? Because not only did Maxwell figure out that time-varying electric and magnetic fields had to move as a wave and move at the speed of light, since light was moving at the speed of light, light had to be an EM wave. That's why they knew by the end of the 19th century that light was a wave. So now people are doing these experiments, and they're just shining light on the material and watching the electrons come off in the same way you might picture a wave of water coming and throwing stones up a beach. And so the bigger the wave, the more that stone should be shot up on the beach. But when they shone red light on the material, no electrons ever came off. Didn't matter how powerful they could make the red light. Green light, the electrons would come off with some speed, not much, right? And they turn up the light, more electrons come off, but not at higher speed. And finally, with the violet light, that the electrons would come off with high speed. And so these experiments were showing that it wasn't really the height of the wave, it was the wavelength of the wave that was causing this to happen. And so this sort of flew in the face of the fact that light must be a wave. And so they were puzzled until this incredible man of physics, Albert Einstein. Of course, some people say it could have been his wife, but you know, let's just not worry too much about that. Let's give it all the credit to Albert Einstein. And you know, the man who probably could have had 5 Nobel Prizes, but for some reason only ever got 1. And we in optics love to know that it's for his optics work that he got the Nobel Prize. And it was explaining this effect, all right? So it's from the experimental observations he pondered and came up with the idea that the energy in light must be quantized. And that minimum energy unit that we now call the photon is a wave-like particle, all right? So that it's both waves and particles all together into this photon, and that the energy of the photon is given by its wavelength. So mostly when we talk about the photoelectric effect, it's usually probably in a quantum mechanics class, not an optics class, and talking about quantizing the energy. But for this talk, I want you to concentrate on what it really said, the photoelectric effect really said, about how we understand light interacting with matter. Because what it says is that one photon meets up with one atom at a time, always. And if that photon energy is greater than the energy the atom is hanging on to that electron, it kicks out the electron with the difference in the energy. But always one photon meeting one atom at a time. And if you change the power, if you double the power, you would get twice as many electrons, okay? Because twice as many photons had found twice as many atoms. But always the energy coming off had to do with that one photon meeting that one atom interaction. And so this is linear optics because it changed linearly with the intensity of the light. And so that's how we now understood how light and matter interacted at the beginning of the 20th century. And then along came this amazing woman, Maria Gabor-Maier. Now she actually won the Nobel Prize, second woman to win a Nobel Prize for nuclear shell structure, which I can tell you nothing about because the last time I studied that I was an undergrad, probably younger than everybody in the room. So don't quiz me on that. She started a whole new field of physics, though, which didn't manage to get a Nobel Prize for, called multiphoton physics. Later on, I'm going to talk about nonlinear optics. And so I'm just going to jump to something that took me 30 years to learn, because I am a slow learner. I was actually at a conference in Russia called 50 Years of Nonlinear Optics when I found this out. There's something called multiphoton physics. And the people who talk about multiphoton physics are the atomic and molecular physicists, because they're actually looking at what happens to the atom or the molecule or the material by this effect. Nonlinear optics people is the same thing, except they watch the light that comes out. That's the difference. It took me a long time to realize that multiphoton physics and nonlinear optics weren't the same thing. But if you're watching the light come out, then you're doing nonlinear optics. But if you're watching what happens to the atom or molecule, then you're doing multiphoton physics. So she was doing multiphoton physics because she was wondering, even though nobody had seen this, she said, surely there must be some chance that an atom could absorb 2 photons. And it shouldn't always have to just be one photon meeting up with one atom. So she was the one. She was working with Max Born at the time, although Max Born is not on her thesis. She got to write the paper in 1931 all by her lonesome, and did the full quantum mechanical theory showing that it's possible, with the absorption, that you could actually add 2 photons together and populate this resonance and excite the atom to here. You could also actually start there and come down to the bottom, and it would have 2 photons down. Now, all of our colleagues in this very popular thing now, quantum optics, will call this photon down conversion now, but she was talking about it way back in 1931. And here's, this would be almost like difference frequency mixing, where you have 1 up and 1 down to populate this level. She's the one who showed that if you're going to have a 2-photon effect, it needs at least 3 quantum levels. That's why we have these funny up and down arrows here. All right? But what's amazing to me is that where Einstein in 1905 was really trying to explain observations that had been made in the previous like 10 to 20 years, she was just thinking this right out of her head, okay? Because this had not been observed. So she just pondered it all on her own. And it comes about, though, from those Maxwell's equations, if we get to them. There we go. So what did she actually, I have to walk this far out of the light. I don't know why, because I have to get close to my equation here. The difference between what I showed before, without really going to the details, was this one little bit here, and this P is the polarization, okay? And so the polarization is that thing that describes, if you put an electric field on the material, how much do you move the electrons from the ions? How much do you set up these dipoles? And there's just a function. There's no reason for it to be linear. It's just a function. And so you can write a function just by some Taylor expansion, which is written out here. Now, this first term we're just going to ignore because this would be a nonlinear material. That means even without an electric field, there would be a dipole there. So that's a different kind of material. That is a piezoelectric material or ferroelectric, whatever. So let's ignore that one. So then we have this Taylor series. And what we showed before, and we got the wave, and what Maxwell did, is he only took the first term of the Taylor series and said to first order, you know, the reaction is just going to be a linear reaction with the electric field. But in a Taylor expansion, you could actually add these extra terms. I'll also say that the reason that Maria Gapert-Meyer went ahead and did it for these resonant interactions of absorption was because you would make these chi2s very big, this denominator functions with omega minus omega naughts coming into there. And so you could make these large enough that she must have thought there was some chance to see it in her lifetime. So for those of you who use lasers but don't study nonlinear optics, this is quite often called the Pockels effect, and this one is called the Kerr effect. Now, the title of my talk is From Nonlinear Optics to High-Intensity Laser Physics. So it's really about this Taylor expansion. So this Taylor expansion is nonlinear optics in that once you can have the electric field strong enough to have a chance to see these second-order, third-order terms, fourth, fifth, then you're doing nonlinear optics, because if it's a second-order term and you double the intensity, you should see the effect quadruple. So that's great. I'm just going to skip right to what is high-intensity laser physics, though. A Taylor expansion only works if you get convergence. At intensities of 10 to the 11 watts per square centimeter, these terms all start to get to have the same order of magnitude, and it no longer is a convergent series. So by about 10 to the 11 watts per square centimeter, this breaks down. At 10 to the 13 watts per square centimeter, the electric field in your laser beam is bigger than the electric field between that outer electron and the ion. All right? And so now that electron is looking at an electric field that's as strong as what's holding to the atom, and there's no reason to stay with the atom anymore. And so, of course, this is completely broken down at that point. Once you're above that 10 to the 13 watts per square centimeter, you are in the area of high-intensity laser physics. So we're going to take you from here to there in this talk. So just for those of you who do want to think about the equations, let's just look at the second order one, and we're not going to deal with the fact that it should be vectors and then there should be tensors, because that's more math than anybody wants to deal with. And so, well, okay, if there's mathematicians here, that's not true, but you know, and the theorists, let's not forget them. But I'm an experimentalist. And the point really is that if you have a 2-photon effect with this E squared, you could have 2 different frequencies. It's a real thing, so add a complex conjugate and go ahead and square it. It brings in a bunch of terms. And one of them is this one multiplied by itself, gives you 2 omega 1. This is what's known as second harmonic generation. You can have the one where it's omega 1 times omega 2, and that's what's known as some frequency generation. This one is omega 1 minus omega 2. And so that's the difference frequency. And so these were all the ones that were shown in Maria Gapert-Meyer's thing. And then this one is where you get back to optical rectification, and you're back to a DC field. And so all of these things can happen just when you allow 2 photons to interact at once. All right, so Maria Gapert-Meyer thought this up in 1930, And yet, as I said, nobody had seen it. And actually, nobody saw it until 1961. Now, the very first multiphoton effect that was seen was actually a nonlinear optical effect, all right? Now, I had my, and I'm sure Ian's, nonlinear optics prof, Bob Boyd, in the audience a few weeks back with me, so he's corrected me already. And feel free, anybody can always, every time I give my physics talk, somebody corrects me, so please keep making this talk better. He pointed out, of course, that he thought that I was pointing out that this was the same thing as what Maria Gayfert-Meyer talked about, and it's not. But the first evidence of two-photon absorption, which is actually harder to see, because then you have to somehow measure that the material's in an excited state. They use fluorescence to be able to tell that. It came out a few months later than this. So it's still 1961. Whether you're looking at two-photon absorption or second harmonic generation, it's 1961, and this one was still first. So what did they see? This is a University of Michigan group headed up by Peter Franken. And they shone red light into a nonlinear crystal. It was quartz. And they, instead of doing ionization like the photoelectric effect and looking for electrons coming off, they weren't seeing absorption. The atom momentarily absorbed the energy of the two red photons and then let go of that energy. But instead of letting it go as two red, it let go one violet photon having twice the energy. So it had energy conservation, all right? But it took the energy of the two photons, simultaneously absorbed, and let go one violet photon. Now, it had a very low efficiency. For those young people, and there's many of you in the audience here, you're not going to believe that we had to use film. Even in my day, we had to use the film, and this is actually before my day. Well, I was born, but that's I wasn't doing spectroscopy. They used film, and so in order to see this effect, which had the efficiency of 10 to the minus 7, they really had to blast the heck out of their film here at the fundamental so they could look down here where the arrow is to look for the violet. Okay? So they decided that on the film, when they saw it, to bring your eye to it, they should put the arrow there to help you see it. Now, you're all squinting, I'm sure, trying to see how small that dot is. I am going to speak at the APS meeting. I'm a little nervous about giving this slide when I do, but this is a paper out of the PhysRev ladder. The IOP people here will be happy to know that this is an APS paper. And film, of course, would have a lot of things that, a hair might have landed on it. There was always these specks in a film that you had to deal with. And so the photo editor at PhysRev Ladders thought that that little dot was one of those specks, and so they erased it. Now, why they thought the arrow was pointing to it, I don't know, because they left the arrow on the picture, but they took away the dot. But we all believe the Franken group saw it. So there you go. Anyway, it's just one of those amusing stories of nonlinear optics. Actually, at that meeting that I told you about, 50 years of nonlinear optics, this person was here. And so for those of you who are so young that you're undergrads in the audience, I want you to know that Peter Franken, I think, is the first author of this paper, even though he was the supervisor, because the person who did the work was an undergrad doing his summer undergrad project for this work. What a great project, eh? So that was seen in 1961. And so then the question is, why did it take 30 years? Maria Gayfert-Meyer told us it should happen. Why did it take 30 years for anybody to see it? And it's really because the laser was demonstrated in 1960. So this is part of my Nobel lecture, so of course I have to give credit to all the people that won Nobel Prizes for laser physics along the way. And so it was Basov and Prokhorov working in Russia at the same time as Towns was working in the United States on the maser, which is the precursor of the laser. M for microwave, L for light, but otherwise sort of the same thing, but technologically much easier to make. So they had it going in the 50s. Art Shallow, and as a Canadian, I always like to point out that he is also Canadian and American, but he did all his degrees in Canada. I was just in Canada, I was telling people that, but even here, I'm going to tell you. And so we like to lay claim to Art Shallow. He later on won for laser spectroscopy, but he's one of the people that really helped figure out how to take maser technology and turn it into laser technology. But it's this person here, Ted Maiman, who was working at Hughes Aircraft. And last night I found out why, because I used to ask the question, I wonder why Hughes Aircraft wanted to have people working on building a laser. There was a huge race going on in the end of the 50s into the 1960s as to who would be the first to build this laser. And I kept thinking, well, nobody at Hughes Aircraft could think it would help them build a better airplane. But apparently, of course, they were building planes for military, and so they were looking for a military weapon, and they thought a laser would be that, and so that's why they were willing to do that. Anyway, okay. But luckily, you know, that's the good thing about the military. They give a lot of money for research. So anyways, it's this man that won the race. His lovely widow has sent me a book about his life, his biography, so I hope to read that soon if I get a few minutes. And so what's the difference, and why was the laser instrumental in finally seeing nonlinear optics or multiphoton physics? Well, if we look at these light bulbs, which are staring at me right now, you will find that they're white light because every color of photon comes off. They come off in every direction, and they don't talk to each other, right? And for that reason, then, the intensity can't be very high. Whereas in a laser, because like I'm showing on the wall here, wherever you're sitting, make sure you see it, not into your eyes, you will see that it's a nice, tight beam. And so it only goes in that one direction, and it's one color. And all the crests, they all talk to each other. So all the crests are together, and all the troughs are together. And so all the waves add coherently and make a giant wave. So I want to go back to that photon picture. If you talk about the power or the energy, it is the energy of each photon multiplied by the total number of photons. The power per unit area is the same as the density of photons, and then multiplied by the energy. And so that's the energy density. And so a giant wave also means that you have a huge photon density. So how is it that the laser led to nonlinear optics? Well, if you go and talk about this kind of light bulb, and you'll see photons are very happy things. And so we have photons of all the colors, but they're not talking to each other. They're just doing their own little dance, that they don't cooperate, and so the intensity isn't very high. Now, if you have taken a magnifying glass with sunlight and tried to, burn paper, did you do that? I did that as a kid. Anyway, you might think it looks like it's going right down to a point. But of course, it only gets to go down to a wavelength of light. I'm sorry for ensemble people if I'm insulting you. But anyway, it only focuses down to a wavelength, which for optics is about 1 micron. All right, but we have to remember that an atom is much smaller than that. It's 10,000 times smaller in diameter. And if you want to have more than one photon being absorbed by that atom, you have to have some chance that that very tiny atom is going to see 2 photons in that interaction time be possible. And it's just not possible with ordinary light. Whereas with a laser, and you'll see them if it's the right one. Yeah, see, they all dance together. And because they all dance together, hand in hand, they know that they can all pack themselves in very tight. And so there's some chance of getting 2 photons in the interaction volume. I want to go back to the idea that Maria Gabert-Meyer was using resonances, all right? And the idea of using quantum resonances means that the interaction time will be much longer. And so the third dimension, 2 dimensions is really the size of the atom, the cross-sectional of the atom. And the third dimension is that interaction time. And so I think she chose 2 photon absorption because there would be the best chance, even with regular light, to possibly see that happen, okay? On the other hand, the first thing that happened was second harmonic generation, and that's a non-resonant process, and so the volume would have been quite small, and yet with the laser they were able to see it. So what has this got to do with me? When I first started my PhD, or shortly after I first started my PhD, Gerard Moreau, my PhD supervisor, gave me this paper written by Stephen Harris, a professor at Stanford. He's still there at Stanford, a lovely man. And I read this theoretical paper. And the idea is that we don't want to do second harmonic or third harmonic. Lasers were giving us coherent radiation, mostly out in the near infrared and then into visible light. But wouldn't it be great if we could have coherent radiation all the way down past the ultraviolet into the extreme ultraviolet, if not the X-rays? And so one of the ways that people were thinking was, well, can we take this idea of second harmonic, third harmonic, maybe fifth harmonic, and can we get it way out there? And so he had these theoretical ideas where he even got to the 15th harmonic. Now, this one may just look like the third harmonic, but if you look, it's the same process. In both this case, he's exploiting a 4th harmonic resonance, okay, and then going down 1 and up 1. This one is a 6th photon resonance, going down 1, up 1, and this will be a 14th resonance. The idea of using the even number of resonances is these would be in gases, and so because of symmetry, the even harmonics are not allowed. But if you're trying to use that Taylor expansion and try to get the 15th one to be big enough, okay, you need that denominator function that's there that isn't already in the 13th, because if it's in the 13th is going to happen before the 15th. So if you use a 14th harmonic resonance, it'll show up in the 15th. You can't make the 14th harmonic because of symmetry, so you don't have to worry about that, and it won't show up in anything below that. So the whole point is to exploit an even resonance to get the next higher odd harmonic. So Gerard asked if I would be interested in doing this for my PhD thesis, and I thought about it, and I came up with the fact that twice ionized nickel would have an 8th order resonance, and I would try to get the 9th order harmonic. So that was what my PhD project was supposed to be. By the end of the talk, I'll explain why I never did that. But anyway, I went on 2 paths. One was to how to make a cold plasma of twice ionized nickel, and one was how do I make an intense laser? Because I didn't just need a laser now. I needed an intense laser if I was going to try to shove 9 photons at once into this very small interaction volume. And so off we went to try to do that. Oops. Let's not go too fast, Donna. There we go. It was funny when I was giving this talk at Livermore. Every time I showed a Rochester laser, it wouldn't actually show up on the screen. I called it the Rochester filter. All right. This is the big laser that was there at the Laboratory for Laser Energetics when I was there. It's a 24-beam system known as the Omega system. It was a kilojoule laser. And so they had big energy lasers, all right? And it would have a nanosecond long pulse. So it did have a terawatt of peak power in the system. And so they had this system. But when they tried to put short pulses down, they found they couldn't do it. Now, one arm of the Omega system was next door to the Omega system, known as the glass development laser. And so you would try things out on one arm before you would put it on 24 arms. And so when you try to put shorter and shorter pulses and wait to see when it goes awry, you would find that if you're trying to get the kilojoule that would work at a nanosecond, by the time you were down to 1 picosecond, you could put in no more than the 1 joule. And so basically, you could have that same terawatt of power, but you couldn't have more, all right? I will point out this last little thing here. There's also, when I talk about lasers, maybe at the end, there's a gain bandwidth. And a short pulse necessarily has a broad bandwidth, and so you can't amplify shorter pulses than what the bandwidth will allow. But let's not even worry about that. Let's not go below the 1 picosecond and the 1 joule. So the question is, what's going wrong, and why can't you get that same kilojoule of energy that's sitting in that laser rod with your short pulse? So I'm going to go back to those of you who were watching the equations and talk about this. I've already said this glass laser is symmetric, so it can't do the second harmonic. And so you just have the linear term and the third order term. We won't worry about the higher order terms. Let's pull the E out. And again, because I'm not doing tensors and stuff, you might think I'm cheating, but it all works out even if you don't cheat. So let's just put the E over here. And now we can just write this as like just a chi, like it would look before, only now it has this extra term here. The index of refraction is related to the square root of the susceptibility. And so you can take the square root. Now, you might think by taking the square root, there should be something in there with the E. I'll remind you, this is a much smaller term than this. We'll use the binomial expansion. That brings in a half. And it just drops down to call something else. The index of refraction is now the normal material index of refraction, but now it's proportional to the electric field squared. That's proportional to the power per unit area, which laser jocks call intensity. Now, Ian and I did get our PhDs from the Institute of Optics, and so we both know our real optics terms. And so the real optics term is a radiance. That is power per unit area, and I want you to know that with my PhD in optics, I know that. I don't actually know when it was that laser people decided that we didn't like that term, because obviously we don't want to say we have irradiant lasers. We want to say we have intense lasers, right? So we just took the term, which really means power per solid angle, and we just started to call that power per unit area. And so that's our intensity, because we have intense lasers. So now, instead of saying N2E squared, we can just say intensity here and gamma. Now, if we have a beam, like the one I'm showing on the wall there, and the ceiling wall over here, the green beam, is a Gaussian beam. And so the intensity on axis is actually stronger than the intensity to the edges. And so the index of refraction is actually bigger on axis than it is on the edges, which means we have a lens. So as the light goes in and gets slowed, the edges, go forward compared to the side, and so you've actually started to focus, which means your beam has become smaller, and so it's more intense. Not only is it more intense, the gradient of the intensity is even higher, which means that it focuses even faster and becomes even smaller and more intense with a bigger gradient. So it actually focuses even faster until, boom, it just collapses, and this is my lovely picture of damage, okay? Now, one piece of damage in your laser rod might be bad, and the distance that it takes here is related to the power, the overall power in the beam, okay? So, but that isn't what they saw when they put short pulses down the laser rods, no. What they saw was an entire row of damage. It would look like If you had clear jello and you put a needle all the way down and pulled it back out, imagine that damage. That's what a laser rod looks like if you put down a pulse that's slightly too short. And the reason is it was Shen and Loy that came up with this model of self-focusing, okay? Because they wondered, why is it? You know, once people started to see this, and many people, I think, saw this damage down their laser rods, someone had to figure out why. So now, not only is your intensity changing with R, but you have a short pulse, so it's changing with time. So I'm just, I'm not, this slide I made myself, so I can only do so much. So I've just divided into 5 segments here. So A is my most powerful segment, the B's are the next, and C's are down here lower. And I've told you that how fast it collapses is the power. So this one would collapse first, and then, by the time you get to B, you're here, C, you'd be here. But of course, if you weren't ever going to collapse at all, you would hit the power that would collapse to here, all the way back, and then it would go back. It's known as the moving focus model because the first one would be out ahead of the peak about here, all right? And then it would break into 2, foci. One's moving faster than the speed of light because this gets to there before the peak gets to there. And so it sort of skis down this hill faster. The other one has to go backwards and then come around later and damage it again because the first time wasn't enough. All right, and so it led to a whole new field of study of self-focusing. It led laser jocks like myself to go, I know the lesson of this, don't put a short pulse down a laser amplifier because otherwise it could cost you a lot of money. So that's where we were in the 1980s. We had big energy lasers and we had short pulse lasers, but you couldn't put your short pulse laser down an amplifier without that. And that's when, in 1983, Girard came up with his idea. So now, when Girard used to show a version of the slide, he always had a picture of me. When I took the slide from him, I put a picture of him. There really are no, as far as I knew until November, there were no pictures of Girard and I together because I hated having my picture taken. I've had to get over that since October 2nd. I will tell you that Girard kept asking if there were any pictures of us, and my husband loves to take pictures, so he got out all his old slides. And we looked through them. It's never going to see the light of day, this picture, but I'm just going to tell you what it is. Because it could be a reverse moment that, when the women are talking about now. So my husband got out all the slides called 1985, 1986, and we're going through them. Most of them, if you know my husband, you'll know they're mostly cars. But every so often, there's people in there. And we all of a sudden see the whole group in the swimming pool. And I went, well, hey, we must be in Snowmass at the Ultrafast conference. I go, why am I not in the pool? I knew Doug wasn't in the pool. He's taking the picture. The very next picture, both Doug and I go, is that me with Girard? Okay, so obviously I'm there dressed like I'm going to the conference. I'm in a skirt, good shoes, I'm ready. And there's papers all over a table beside the swimming pool. And there's Girard on the other side of the pool, obviously in a swimming suit, but you don't see that. So you only see him naked up. So I'm not going to show that picture. I don't think he's going to show the picture. So that's the only picture that I know of the two of us from back in the day. So anyways, but now we've had our picture taken together, all from the same week. This is actually the same day, just so you know. I couldn't decide which one I liked better, so I've left them both up there now. So this is us at 10:30 in the morning of December 10th, and we're in our red chairs, and we're there to practice how to take the medal from the king's hand with a stand-in for the king. We're always having a good time. And there we are midnight of that day. We've gotten our medal, we've gone to the banquet, and we're just having a ball at the ball. So what's the idea, and why is it that, and you'll also notice that the Nobel Prize winners have now turned into color, where they were all black and white until us, but So what is it we try to do? So I should tell you that what we really wanted to do is how do you get intense light? We need this great photon volume. And so I am going to give you part of my public lecture too, just in case there's people who don't do optics. It's one of the things that I still find amazing, is that if I actually make a 1-second laser pulse, right, if I can do it, there we go, on the wall. Does everybody see it? I could do it right here on the screen. There we go, 1-second laser pulse. Now, say this was a window, and say the moon was that way. I have no idea where the moon is. And I sent my 1-second laser pulse to the moon. I still find it remarkable that the beginning of that pulse would be 2/3 of the way to the moon, right? It took me 7 hours to get here, and yet from Canada, and yet light can get 2/3 of the way to the moon in just 1 second. It's remarkable. So now, this is actually about a milliwatt, and it doesn't hurt me at all, right? Every second, that's a millijoule of energy hitting me. And so it seems like nothing, right? I'll tell you, the paper that I got the Nobel Prize for had no more than a millijoule in it. The light that actually will carve your cornea and do surgery for you is no more than a millijoule. The light that carves the glass in your cell phones is no more than a millijoule. And yet it can, you can feel a millijoule all the time and it doesn't hurt. And the difference is that the laser pulses that we made were 1 picosecond, 10 to the minus 12 seconds. And instead of stretching over 300,000 kilometers, we took all those photons and they're in 1/3 of a millimeter. And so it's the photon density that's so much higher. And so it actually just comes in, and sometimes it's the energy that matters in it, but sometimes it's energy per unit time. And now these lights can just come and smack those atoms, and those electrons have to fly. So I always say I created a laser hammer. So here's the laser hammer. It's short pulse, it's high energy, but you don't want that laser hammer in the amplifier because it drilled holes in the laser amplifier. Very simple idea. I'm amazed that we got a Nobel Prize for it. But anyway, I'm not giving it back. We have this short pulse, low energy. We know we can't put it in the amplifier. Here's the beautiful idea. Stretch it out and make it long. Go ahead and amplify it totally safely. Compress it to make it short, and you're done. Seems pretty simple. Took me a year to do. So what were we going to do? So here's this beautiful laser that convinced me to work with Gerard's group, a lovely dye laser. It's even a shorter pulse than what I created. It's 100 femtosecond pulse. But the laser that I'm talking about here, neodymium YAG, is this one back here. It's an infrared. You'll see that you see no beam here because it's infrared. Our eyes can't see it. The camera can't see it. This is the same process that the Franklin group saw. They're turning it into 2 infrared photons become a green photon. They could do it with 10% efficiency. This is a green mirror, which means the infrared is coming through here. The other thing to notice, though, is there's simply no more room to build a chirp pulse amplification system. Okay? So they carved out this little bit of room back here for me. And there, should be here. Hello. No? Here we go. Here I am. So young. A few things to notice. One is that, of course, I'm sure this is true every time you get your picture taken here. Although I always have my picture taken here now in 2 labs without safety goggles on all of us. But anyway, usually if you look like you're near the lab, you better have safety goggles on. You'll also notice, though, that they're not actually in the frames, just the frames, because the photographer didn't like the fact that you couldn't see the eyes through the green laser goggles. There won't be any laser on. You can't tell if an infrared laser's on or not. I think I'm actually just holding the fiber. He wanted me to tweak some knob. I said no. Here is the fiber for the stretcher. It's 1.4 kilometers long. I do want all the students to understand why I had 1.4 kilometers. Because you might think, being a Nobel Prize winning PhD project, that I, dutifully sat down and calculated exactly what I needed, right? But no. Gerard, who was very good at begging for money, called down to Corning, which is just an hour south of Rochester, known for its beautiful glass ornaments, but also known for making optical fiber for communications. He knew that they had this new specialty fiber that did work at 1 micron and say, don't you want to donate to this really important project we're going to do? Corning very generously donated 2.5 kilometers of optical fiber for us. Unfortunately, when they did that and spooled it, they spooled it such that you couldn't get to the one end, and I had to get to both ends. So I had to spend a day of my life spooling and unspooling and respooling. And when I put the light down the fiber, it didn't come out the other end. And when I picked up my IR viewer, there it was coming out almost right in the middle. 1.4 kilometers is all I had as the longer of the 2 halves. And so that's why I did the experiment with 1.4 kilometers. It was long enough, I got a Nobel Prize. Anyway. So now the question is, what do I need this fiber for? Partly, this is all the space I was given in this lab. You can see on the other side, I was crowded in here. So a very lovely woman in my group, another grad student, Shou Xiaoxian, she was willing in the middle of the night, because of course you can't do this with plant ops, went through the air ducts with the fiber and brought it down to the other end of the laboratory for laser energetics, where we had a new blank empty lab where I could build the amplifier. I am way too claustrophobic and afraid of heights to be the one who goes through it. But luckily this other woman who had nothing to do with the project nicely did that for me. Afterwards, I realized it was so hard to tweak it without having any way of knowing if the power was still coming down there. She went through the whole thing carrying a BNC cable with her, so I could now easily measure the power in my other room. So that's the first thing. It worked out well that I needed a fiber to get the light from one end of the laser lab to the other. But that's not the other thing. There's 2 things I need to do. I have to make colors and I have to stretch the pulse. So first, just to tell you why it is that a short pulse necessarily has a lot of colors. It's Fourier transform theory, for those of you who know. And the other thing, though, is if you had a laser like this that's only one color, it would mean, I don't know, can I find the green? Anyways, it would go on forever. But now, the beautiful thing about lasers is you can say, let's all go together, and they all can talk to each other. And we can have all the colors start right here, but then because they're all different wavelengths, they come apart, and eventually you have your troughs meeting, no, that's your trough meeting a peak, and the black is the sum of these colors. And the more colors you bring in, the quicker it goes to a 0 and the shorter pulse you have. And so that's what Fourier transform says. If you want a short pulse, you need a lot of bandwidth. Now, the pulses that I was using out of that YAG were 100 picoseconds, and I wanted single picoseconds, so we had to make the colors. If you have as short as you can, this is a picture of a Fourier transform limited pulse. And what that means is that even though you have a lot of colors because it's a short pulse, they're lined up such that the peaks are equidistant apart. But now if I'm going to go down the fiber and all these different colors travel at different speeds, there's a phase as you go down the z, and the phase velocity is the speed of light c, but divided by the index of refraction, and we must remember the index of refraction is frequency dependent. So I've drawn that here. So if we talk about the phase now as a function of frequency and take derivatives so we can have something like the Taylor expansion here, and we just look at this first term, that tells you the speed that the peaks travel. Now only the people like here that I've seen beautiful attosecond labs here, so they care, right? The people that are trying to do attoseconds care that their 5 femtosecond pulses, that their peak is lining up with this. The rest of us don't care. But what we care about, the rest of us, is what's happening. Does this pulse get to stay the same short pulse? No, and that's because of this term. This is the term that says that there's dispersion of that group velocity, all right? And so if you look at that, then all these colors each have their own group velocity, and so red comes out ahead of green, comes out of the blue. And so unfortunately, because we plot time this way, which really bothers me, I usually plot it negative, but I stole this from the web. This is actually the front of the pulse. Because again, if you get your PhD from Rochester, you will know that light only travels left to right. So that should be the front of the pulse. So it bothers me every time that this is the front of the pulse. But anyway, you'll see this beautiful chirp. And so what is a chirp? A bird's chirp has the audio frequency change through the note, right? And so chirped pulse is one where the frequency changes through the pulse. We could have called it stretched pulse amplification, but doesn't chirped pulse amplification sound so much better? So that's what we want. Now, what did we do to get it? Oh, did I even bring my slinky? Because I'm going to get Ian to help me with my slinky explain this, if I brought my slinky. You never, oh, don't tell me I don't have my slinky. That won't be good. No, here it is. Don't you always travel with a slinky? OK. Do you want to help me too? Could you just hold? You can just hold it there if you want. But we have to do it in the light, and you hold it back here. OK. OK. So now, really useful. There we go. So now light would not bend like this, OK? But that's all right. Don't worry about that. So now you'll see the way they're holding it. These are going to be my phase fronts, and that's what gives the wavelength. So this is now Fourier transform limited pulse. It's as short as it can be because all of those waves, fronts, are equidistance apart. But now if you remember that what I said about self-focusing is that the index of refraction now, instead of changing with space, is changing with time. And so we have this pulse in time. And so the guy at the peak is actually moving slower than the back or the front. And what does that do? So because we know light travels this way, that's the front of the pulse. And so they're going to stand still, but they're going to be actually the ones traveling the speed of light. And I'm at the peak of the pulse. Yeah, pretty close. I'll be on the other side so you see. And so I'm at the peak of the pulse traveling slower. So if I travel slower, it's like me going backwards. And if you see that I've now made these wavelengths come farther apart, and this is how we make red at the front, but these got squeezed together, and so we make blue at the back. And so it is this nonlinear optical process in the fiber that actually creates new colors as it goes down. OK? Thank you so much for helping me with that. Like when I'm in Waterloo, I actually have weights, and we lay it down. But thank you. I didn't want to carry weights with me. So that's how we make the colors. Now, there's a problem with that, and this is why most of the time, unless you're doing fiber CPA now, you don't use fibers. And this is because if you watch, it starts at the frequency, it goes red, goes back to the normal frequency, goes blue, and comes back. And so you have this weird S shape. Very hard to do something with that, OK? So, but then, 1984, now remember, we did our work in 1985. 1984, those of us in the ultrafast community, there were people working on taking these YAG lasers that were 100 picoseconds and trying to make single picosecond pulses of them out at 1 micron. And they did fiber optical pulse compression. And so they noticed that the spectrum got wider from the process I just explained. But there's also dispersion in the fiber. And that's what I just showed, how the different group velocities go apart. And so now it gets mapped on. The spectrum will eventually get mapped onto time here. And there was, in order to get this almost linear chirp, instead of that weird S-shaped chirp, there was an ideal length. That's probably what I could have been calculating, but didn't. Ideal length to do it. So here was the thing, just ready to go, and it was about this time that Gerard told me his idea. Now, he had the idea in 1983, but this was the thing that really said it's time to go. We've got everything we need for chirped pulse amplification because we've now got all the colors we need. It just turns out that in order to do beautiful compression, we need to stretch the pulse anyway. So what's left to do? Let's just put the amplifier after our fiber stretcher and then compress, and it's done. So here, just to tell you about laser amplification, it takes energy to go in. Well, that was fast. And so then you now have this light pumped up. Glass lasers will hold on to that energy, and that's why they are big storage energy. Now watch, the smiling faces will come in, and those are the photons, remember. When the photon meets the atom, it says, hey, I'll take your energy because we have the very same energy. And we'll walk hand in hand, but you lose your energy. Those two photons go on and find their own two atoms, and they do it again, and they become 4. And then the 4 becomes 8. Don't you? There you are. So, but you'll see that by the time it gets to the end, although that's exponential gain, it's left most of the energy behind. This is not efficient. Nobody wants that. Now, in a normal laser, we have mirrors sending the light back and forth until the last path actually comes along and sweeps that energy out. For laser amplifiers, you actually have to keep blowing up the beam. Each type of material will have its saturation energy. It will tell you how much energy per unit area in a pulse it takes in order to sweep that energy out. And so to get more energy, at the end of your amplifier, you must make your beam bigger and then go through the next amplifier until you get that same energy per unit area, and then you make your beam bigger. That is why the Omega laser is a huge laser in order to get to that kilojoule of energy. So it is the material and the energy storage that determines the energy per unit area. It is the self-focusing nonlinearity that says what the density of photons can be, so that's energy per unit volume. And so that's what tells you how long does your light have to be. And so for glass, it should be a nanosecond long so that you have no self-focusing happening. Now, I only had 1.4 kilometers of fiber, so we stretched to 300 picoseconds. We didn't amplify all the way up. It was all OK. All we have left to do is compress. So we use a pair of parallel gratings. This is Tracy. Tracy's name should be there on the physics one. Come on, Tracy. Where are you? Well, just believe me. I don't know. Somehow, some of my slides. Let's just go one more. Oh, there it is. Oh, excellent. I knew he gave him credit. So way back in 1969, he came up with this idea that 2 gratings parallel would be a compressor. Why? Gratings have a different angle for different wavelengths of light, just like prisms. And if you watch, the red was out ahead of the blue, but the red has to come all the way back here and out to here by the time the blue just gets to here. And so if you set your gratings just right, you could have the blue travel less distance than the red by just the right amount. So at the end, you have a nice short pulse. Now, technically, we don't do it this way because that would be a line. And so we actually send the beam back when it's only half compressed, go back through. We'll have a nice round beam, and the pulse is compressed. I'm just going to say that this is why we don't usually use fibers anymore, because since then we realized you'd use a gratings both with stretchers and compressors, because if we change signs here with a fiber, we don't change signs here. And a third order, we can't correct anymore. So our pulses are never transform limited if we do that. Here's the work out of my thesis and out of the first paper. All we did was take the 100 picosecond. We went through that fiber. This is an artist's rendition. This is not the way our chirp really was. There is certainly a weird type of gain narrowing, because the red is out the front, and we are going through at the saturation energy. The front will see more gain than the back. And so we get this part of the spectrum peaked compared to that. Now the fancy dancy great big ones actually do double. They do compression, then they do compression in the opposite direction for the final amplifier. So they get the red ahead of the blue, and it all kind of works out nice. OK, we go down through here, and we're back to having a short pulse. This is the work we did on a Thursday night with my colleague Steve Williamson. He had a street camera. I had no way to measure it. I set up the gratings with the oscillator pulses, but I had no way to measure the 10 hertz. Or this wasn't, yeah, this was 10 hertz. 10 hertz pulses. And so Steve Williamson and I spent one night together and took this result. So this showed that it was 2 picoseconds. That's often etalon to show that it was. All right, so back to the, what did I do for my PhD thesis? Gerard always says how I said that a CPA would not be a good thesis. And I was right, because I wouldn't have been allowed to do it for my thesis, but he keeps ignoring that. And then actually, since then, I realized he's actually not on these, his name is not on these papers. So he might have forgotten I had to do MPI for my thesis. I don't know. I'll tell you, well, I haven't got to, I'll still get to why I didn't do harmonic generation. But Si Long Chun came down to do a sabbatical with us and convinced Gerard to let me do multiphoton ionization for my PhD because I was running out of time. Luckily, it was the United States where we could take almost forever to get a PhD, unlike here. But even so, I was running out of time. So the idea is the same as sort of the, a multiphoton version of the photoelectric effect, only in the gases I was using, it probably would have taken 11 photons. So we expected to see intensity to the 11th order process, and that's not what we saw. This is because we had made such an intense laser, we were no longer needing the photon pitcher. We weren't putting the kinetic energy into the electrons. The wave was so strong, it was back to just being a wave. And you could think about, instead of putting the energy into the kinetic energy of the electron, the wave comes along and warps the potential energy of the atom holding onto the electron. And so it actually bends it over. Now, it'll bend it over, you know, every 2 femtoseconds it does this, but it's getting bigger as it goes. And by the center, boom, it's all the way over. And what our work showed was that it basically came all the way until the electron was no longer trapped, and out it went. And so with the CPA, it once again changed how we saw light and matter interacting with each other. So this is no longer nonlinear optics. This is in the realm now of high-intensity laser physics. So just to tell you where we went with that. Other people went. Oh, here it comes. All right, so this is 1988. This is the last year of my PhD. This group in France sees the 33rd harmonic. So why do the 9th harmonic? That's really, you know. I also hadn't figured out how to make a twice ionized cold nickel plasma. So there was all kinds of reasons not to bother doing that PhD. But if you read this, it just sort of says, you know, we don't know. We weren't expecting 33 harmonics. And that it's happening very close to that of multiphoton ionization. And so people knew it had something, that there was some connection, but we didn't know why the harmonics were coming out. As people here are well aware, we're well above the 100th harmonic, and this is how we make attosecond pulses. I'm not going to explain it because I'm here at Imperial College. I didn't explain it when I was in front of Paul Corkum either. I told everybody in that room, if they haven't already heard about it, well, shame on them, and I'll say the same here. There's enough people working on this here that you should already know about this. But again, it's from our new understanding of how light and matter interact at these high intensities that have given us X-rays out to the water window, and coherent X-rays out to the water window, and attosecond pulses. So here's a slide that Gerard has shown for quite a few years now. It used to be a straight line, right? So we should have been up here by now. It is curved over. If you watch Gerard's Nobel lecture, though, because it took me a while since I took this slide from him, his does not curve over as much as mine. And yet I knew he wasn't, I know. I knew he wasn't lying, though, because it was, you know, it was the Nobel stage, and I knew he wasn't lying, so I had to think a little bit about it. But if you go back and look at his slides, he just slid the 10 to the 25 up to here. The other numbers stayed the same, but he just slid the 10 to the 25 up to here. No. So here we go. Livermore was the first place that actually got the petawatt to go. So they are the ones who took the kilojoule laser and got the picosecond pulse with it. Chios is Gerard's laser in Michigan. Now, the difference, they didn't get as high as a petawatt, and so why are they 2 orders of magnitude more intense? Again, it is light per unit area. Livermore was doing it for fusion, and so their focusing lens had to be long. It had to be outside the fusion chamber so they didn't block all the other beams trying to get to the target. And so they weren't trying to focus down a single wavelength. Gerard's group in Michigan went ahead and used F1 optics. They also showed, though, that the beam quality isn't great, and so they have to make sure they use movable mirrors and stuff in order to get back that beautiful beam spot that they did, and so 10 to the 22 watts per square centimeter. Now, one of the goals of this whole work trying to get up here is this one here. This is breaking the vacuum. This is what the vacuum is made actually up of material, positrons and electrons together. And can we take the matter and the antimatter and blow it apart? Well, supposedly if 10 to the 29, you would have the same electric field in your laser that are holding that particle and antiparticle together. And so wouldn't that be wonderful to create something out of nothing? Now, I'll tell you that I personally think it's going to take another Nobel Prize winning idea more than CPA to get us there, but nevertheless, we're on our way. So some of the lasers, North America, sadly, has pretty much given up compared to Europe, and certainly Asia is the leader now in this field of trying to get lasers out there well above a petawatt. China announced last year that they are building the 100 petawatt system. So we will keep climbing, although it is getting to be quite large lasers and quite a bit of technology. And of course, most of the lasers don't talk about their beam quality because there is still some thermal issues that have to be worked out. So let's just go back. I don't know how much time I have left. I'll be careful. Okay, why can we do laser surgery with it? This is because a continuous laser will use a thermal process. It will be absorbed by some, the light gets absorbed, the stuff heats up, the heat spreads out. If you use short pulses and use the impact one and not a thermal process, you don't have to worry about that thermal spread. Do I have time for this? Do we want to see this awful thing? I personally find it gross. Okay, so that's docking. That's obviously a medical term. Here comes the laser, though. That is the CPA laser. You'll see that this is George's video, and so we don't even show the excimer laser doing the actual carving of the cornea. This one is creating the flap, and so it's inside the surface of it, and the beam is being raster scanned to make all of those many, many damaged spots. This I can watch. I have no problem watching this. It's the next part that I really have trouble with, so I won't watch. So this is where now, I can't imagine 24 million people have allowed this to happen to their eyes, because a surgeon now comes in while you're watching. You can't be asleep, and you actually lift that thing up. I find it quite gross. All right, and so that's all that the light does. People have given me so much credit for every eye operation they've ever had, and really all that the CPA lasers are used for in eye surgery is to create, isn't that gross? Create the flap, okay? So it's basically machined under the surface so that it's made this beautifully precise cut. Although, as I understand it, half the surgeries still have a surgical scalpel do the flap cut. Not every surgeon wants to use the laser. I know, like, how can you watch that? I don't know, like, what is happening on your own eye, I would just freak right out. All right, here's the last application. This is the one going forward that I think will be most exciting, is that when we talk about the fact that the electron goes out, it's going out at a tremendous force, right? That electric field is a tremendous force, but you have to remember that it comes right back in 2 femtoseconds later, and so the electron wiggles back and forth. So we in the community call it the wiggle energy, but every time there's a kinetic energy, there's a corresponding potential energy, which is known as the ponderomotive energy here. And so for the laser pulse, it actually is like a mountain, okay? And if you turn that mountain up so that the electrons sort of ski down that mountain, turn it upside down and have it be like the hull of a boat, all right? So the laser pulse going through a plasma is the same as the hull going through water, pushing the water off of it, and it makes a wake, right? And then you can ski off that wake, and you could accelerate. It's the same as skiing down any hill, if you can stay on that wake. Satoshi Tajima and Dawson came up with this way back in 1979. Again, it's a theoretical study, so they didn't have to worry about technology. But they said if the laser pulses got strong enough, we could accelerate electrons. So, and possibly even protons. And so this is work that's going on. Can we beat CERN? Can we beat hospital scale accelerators so that we can maybe have radiation treatments, proton energies high enough to go further, deeper into the brain and possibly get to brain cancer that we can't get to now. So just a couple of pitches. Oops, no, let me go back one. It doesn't want it. There we go. Okay, I'm just not going to show you. You saw how much fun I was having with the king. The night after the December 10th, December 11th, and all you guests go home, just you and your spouse get to go with the other laureates and their spouses to the palace. And we once again dine with the royal family, and that's their dining room that they get to eat at. Isn't that spectacular? And so I like to say somehow I went from just working hard on a PhD project to landing in a fairy tale. So thank you very much for your attention.
It's gone again. Oh. It's okay, it's okay. Hello everyone, I'm Michelle Doherty, I'm head of physics. I was really honored when Ian asked if I would give the vote of thanks to Donna. But before I do that, I think we might have some time for questions, if that's okay. So, does anyone have any questions? If we can see the hand, these lights are a killer, aren't they? I can't see any hands. Ian, you must have a question. I saw you writing something down, so. There's a question there.
Safe, Ian.
Yes.
Hi, I have a funny question.
If you hold on 1 second, there's a microphone coming to you.
Hi, I have a funny question. So could you tell me who made that wiggle photons animation?
So let me just go back to, because maybe I'll just use these ones here and see if I can get to the right people. Yes, I had, let me think, everybody, these are the people that built the laser with me. These are the people that did multiphoton ionization with me. And these are the people at the University of Waterloo. So right after I won the Nobel Prize and they came and they said, what can we do to help? I said, you know, I've seen some great lectures by Nobel laureates, and they seem to know how to make PowerPoint slides, and that's something I have no clue how to do. So can we help with that? And so they worked away. Some of the ones, this is why I do the demo with the Slinky, because they really couldn't figure out how to make that figure for me. And I went, all right, I'll just do it with the Slinky. And, but they're the ones who do it, not me.
There we go, John. And Stephen as well.
Donna, great talk. I have a sort of an interesting question, I hope, which is when you were working on your PhD and you did that street camera measurement and you sort of seen that you'd nailed it, was there any inkling at that point that the breakthrough you had made could, lead to a Nobel Prize? Or really is that something that one could not really predict? I mean, did you have some sort of gut feeling that this really was something that could be very huge? Or, I mean, obviously all the applications have followed since.
I don't think we could know the applications. I think we knew it was going to be big, and I know shortly after we did it, what was called, FIO was called, just like I said, was the annual meeting. They came to us saying, we've heard about it, and we'd like you to do a post-deadline paper. And Gerard and I ran around, and he goes, what's the word for 10 to the 15? You have to say that we're going to put this into a kilojoule laser, get your picoseconds. That's 10 to the 15. What's the word for that? And I went, I don't know what the word for that is. And it was late at night, and the laser lab had a little library, so we couldn't go to the real library, so we were just running around this, trying to find the word for petawatt. So we knew that it would be big for that, but we also probably thought at the time it would stay in the big labs, like the Laser Lab, Livermore, LOA, here, Rutherford, those kinds of places. And so we knew that it would have an impact, right? But I don't think if Thai Sapphire hadn't come along, if Peter Moulton hadn't figured that out, it wouldn't have been in labs like yours, right? And it wouldn't have exploded quite in the same way. And I don't, we wouldn't have had laser eye surgery with those great big lasers and things like that. So I think it's hard to picture how big it was going to be. But I think we knew that it had revolutionized from nonlinear optics to high-intensity laser physics, so I think we knew that. But.
Okay, thanks.
Stephen, one in the front here.
Thank you for a stupendous talk.
Oh,
your
thank you.
enthusiasm for the subject and your work and your clear ability as an experimentalist is really evident. But you will know that you are still that rarest of individuals, a female Nobel Prize winner in physics. Now, I know you don't really want the burden of speaking for your
Have I said that often
gender.
enough? Okay, yeah.
But clearly, we live in a society and in a world where too few women are still coming into physics. So I wonder, do you have a message for how we might address that? And particularly, I wonder if you have a message for your male colleagues about what we might do in order to help address that.
I have thought about that over the years. I'm going to tell you two different sides to the coin. Not all women like to hear what I say. But anyway, early on, when people started talking about it long ago, I would go, well, why do those of us that are in here want more women? We'll lose our special status. And I did actually say that to a group of students who, they bring in students from around the world for Nobel Week, and then they're at the Royal Swedish Academy party the night before, and they were all meeting me. And I said, I have to admit that I usually felt like just one of the guys, but I also knew I was the special one, and I liked to be in the special one. And they were also kind of looking shocked at me, and then right then a woman walks right up to me, and she said, I just want to congratulate you. You're just so special. And I said, see, why do I want to give that up? And now on the other side, when I've thought about why is it, because I can't imagine going into the medical field, because you can see that I didn't even watch that, and I certainly wouldn't have it done to my eye. I don't even like walking into hospitals, so obviously I would never go into the medical field, and yet women now outnumber the men in the medical field, and I hope we're all worried about why men aren't going to medicine. I hope we're all worried about why men aren't going to university. So the question is, I have female surgical friends who said they've felt all kinds of problems with the male surgeons, right? That they're certainly, I've never felt that from male colleagues at all. So, it's not that I don't believe in implicit bias. I think all of that exists and there's problems. But women will fight against them when they truly want to. And I think one of the big problems is that very few people go into physics. Men or women, very few people go into physics. And the question is why? And I think society still to this day doesn't put a huge societal benefit on being a physicist. Most families, parents will probably still say, become a lawyer if you're good at arts, or become a doctor. Medical doctor, that means, over here, because those are the professions that society values. And so until we get around, now I think in the high-tech world, it's coming around, and there's enough physics geeks out there making really good money that I think parents will start telling their kids to go into physics. And when they do that, the women will hear it as much as the boys and girls will hear it equally. I could also say another thing, which I won't because I'll get myself in too much trouble. But anyway, go on. Okay, I will. You know, I have said, because I've gone through many, many science graduations at Waterloo, and optometry is like 90% women. I go, what the heck? Biology is like 75% women. It's just like women, 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 women over the, you know, and this is a science. And we talk about women in STEM, women, women, women. And finally, I started to see them line up, and it's all guys. I went, oh, good, here comes physics. And then I say, you know, I kind of think we have to leave physics to the men because it's all they've got.
Ooh. Ian, do you want to follow that up with your question? Okay, I think, yeah, Ian's changed his mind about it. Okay, so we really appreciate Donna visiting us today. We know it's been an extremely busy time for her since she was awarded the Nobel Prize. We're really excited that she decided to fit us into her very busy schedule. She's an inspiration to all of us, and I'd like to thank her on all of our behalves for the fantastic lecture today. Thank you very much.